I'm going to introduce Sara. Sara Erickson here is going to be presenting next. We're going to be talking, or she's going to be talking about her all-electric multifamily developments. She is the project manager over at Charities Housing. Sara has over 20 years of experience in real estate development and investment. 13 plus years were in market rate commercial real estate development, and the last 7 years have been in affordable and homeless housing development in the Bay Area. Currently, Sara is Senior Project Manager of Real Estate Development Team over at Charities Housing. Charities is focused on developing affordable housing for the most vulnerable populations, primarily in Santa Clara County. Thank you, Sara. Okay, we can hear
Hello,
you.
everyone. Can you hear me?
You sound great.
Oh, fantastic. Thank you, Hannah. That was such a great presentation. Thank you for the introduction, Sean. Well, let's get started. Hi, welcome. I'm Sara Erickson, here to talk about why it is more cost-effective to build all-electric buildings in affordable housing. As I believe we all know now, electricity powers the most efficient technologies available and is the cleaner energy source. We're in a climate crisis, and going all-electric is our future. Just so you know what you are getting yourselves into, this is a quick overview of the topics I'm going to cover. I'm going to walk you through the cost-benefit analysis that I have participated in, specifically on a project called Hvac Gardens. This was my first all-electric project, as it was for nearly all of the design team, with the exception of Sean Armstrong, who was our energy consultant and a pioneer in this field. So many lessons were learned that will help me and all that participated to be more efficient in the future. I am a developer on the real estate team at Charities Housing, and we are committed to doing all electric on 100% of our projects. Our last mixed gas electric project just started construction. All future designs for our buildings will be all electric, and we have one under construction currently. Gas is being phased out. It's not sustainable. The writing is not only on the wall, but becoming endorsed more and more by local jurisdictions with breach codes and whatnot. We want to be early adopters, as it's better to get ahead of the ball and work out the learning curve challenges before it's mandated statewide. Electric is the cleaner energy source, and cost-wise, there are advantages to building all electric. This case study I'm presenting today is from my experience as the primary and lead project manager on Hvac Gardens when I worked at Resources for Community Development. As part of the development process, we considered if we could make this project zero net energy. Listed on this slide were the main goals we pursued in our analysis. Financial viability being the biggest barrier to overcome. So you understand the overall project concept, here are some salient details on this slide. We were not fully committed to all electric because we wanted to understand the cost impacts of making this choice. After entitlements were approved in July 2017, we started the schematic design process. Then we got into design development, and that's when we really took the opportunity to analyze the costs and benefits of different building systems in an effort to see if net zero energy would be viable. We wanted to push the envelope to be as efficient as possible, but also fiscally mindful. Ultimately, the project ended up with an over 40% increase above code in energy efficiency, and it will be certified Green Point rated platinum, well in excess of the minimum points required. We did not end up with a net zero energy project because unfortunately it was not financially viable due to a variety of constraints. But as I said before, there were many lessons learned. Going all electric was an easy decision after this exercise because the cost hurdle was relatively minor and the benefits outweighed the risk. Here's a rendering and a view of the original site so you can get an idea of the scale of the building. It is currently under construction, due to be completed this summer and fully leased up by the end of the year. It's so exciting. We're about to house 71 different households. So getting rid of gas infrastructure means figuring out which all-electric domestic hot water system to use. These are the options we considered. Which one do you think we chose? A central electric system was the second most expensive option. I learned from Sean that a centralized system, due to the circulation of the water, loses about 30% of its efficiency heat loss, and hence it increases hot water energy use by 30% over a decentralized system of tanks. As a result of a larger solar array would be needed versus one for decentralized systems. So the increased solar array budget and costs to accommodate the recirculation offset was factored into the cost benefit analysis, causing this to be more expensive than the individual water heaters. If we had not factored in the added solar costs, then this would have been the most affordable option. So I encourage developers to take that into mind when you're doing these cost benefit analysis. Centralized systems get tied into the house meter, which we, the owners, pay for. The solar arrays we install offset the house meter. So even if we can't offset any tenant energy, we are motivated to keep the house meter costs down. Hence, this was an unattractive option. This is the option we selected, individual water heaters. In a very thoughtful exercise of trying to weigh all the pros and cons, we also attempted to consider the maintenance costs on the operating budget and tenant impacts. Central systems require routine maintenance even more so than individual water heaters. And typically you need to hire a third-party vendor to do the maintenance rather than the maintenance staff, who often are not trained to maintain central systems. When an issue occurs with the central system, all residents are impacted and lose their water until repairs are made. It is not clear yet if these individual electric water heaters are as easy to maintain as conventional gas water heaters. With gas water heaters like the ones most of us have where we live, technically you're supposed to drain them out every so often, but no one does, right? And they last a really long time. They seem to be just fine for at least 10 years. There aren't many buildings in operation to learn from yet. We are assuming reduced maintenance costs, not needing a third-party contract for repair maintenance on a central system. Having lower operating costs means we have higher revenue to leverage a higher loan. This is a huge benefit. There was a lot of concern from the property management team about the unknowns of the electric systems. Ultimately, property management realized that we are in a time of adopting new technology, and the maintenance teams will need to be trained accordingly. RCD and Charities Housing do not yet have the data on operational outcomes and efficiency, maintenance issues, warranty issues, etc. I found that most affordable housing developers who are more and more getting on board with doing all electric design are doing a multitude variety of different designs on different projects, so that when the buildings are in operations, comparisons can be made to understand if one system is preferred over another from an operating standpoint. Sean, being the pioneer that he is in this field, is one of the few that I've found that does actually have data on these, as he started designing all electric buildings so long ago that there are many in operations, which was helpful to get those contacts so we can connect our property management teams to those projects so they can share lessons learned and feedback. Here are the costs for a conventional gas central boiler system. Note that the gas infrastructure costs were greater than the boiler equipment costs. Also, please note under the demo, offsite, and site lateral line items, we have pricing from Walton's Furman GC as opposed to the actual GC we used on the project, Robert Sobayashi. And this is because Sean had to go find detailed comps because our GC couldn't get his sub to price out a detailed estimate of the non-equipment related costs. Sub didn't have the time or energy. Subcontractors were in such high demand. There was a major shortage of labor at that time. And in general, it seemed the GC team was primarily pro-gas because it was low-hanging fruit, the easiest thing they knew how to install without a learning curve. Are the comp Sean got for these line items 100% accurate because they were based on another project? There is some room for error there, I suppose, but everyone on the design team agreed, including Robert Sobayashi, that Sean's infrastructure estimates seemed very reasonable. Factoring in the infrastructure costs, all three domestic hot water options were somewhat in the same ballpark. Here is a summary of all costs. From pricing standpoint, they're so close that we could have picked any of them. It was frustrating. Our GC didn't really try hard to get an accurate, detailed gas infrastructure estimate. He gave us a lowballed amount without backup, I think, because he wasn't very enthusiastic about doing it, just to be straightforward. They were working on a few other all-electric projects, and they were having some challenges due to learning curves of those design teams. So I can understand his resistance somewhat. If I were to have made a decision based on the GC's preference and used his lowball number, then worst case scenario, we paid a premium of $80,000 to go all electric. But I don't think I think he lowballed it. So I'm just, pointing that out. But in the whole scale of a 41.5 million GMP contract of total hard costs, to me, it was worth it for a lot of reasons. The new skill set we would acquire when REACH codes are coming down the pike more and more. Our tenants won't be exposed to gas in their kitchens, better indoor air quality, the climate benefit reasons. If there's an earthquake in the future, our tenants will not be directly at risk of a gas line break. Another all-electric decision that was made was to add an extra transformer for about $50,000. Our electrical load for the building was at near capacity with just one transformer. The MEP suggested we scale back the electric load and revisit our electric building systems just to alleviate any risks. After months of evaluating options and making final selections, I didn't want us to go back to the drawing board. $50,000 would be less than added design costs and time delays to reduce the electrical loads. Another consideration I had was future loads that the building might have. I didn't want the building to be at capacity in 20 years when it was time for a remodel. That happens so often these days when you're trying to convert existing buildings to all electric, and it's the electrical loads that prevent you from being able to do that, and the cost to upgrade the systems. This happened on one of my Antioch rehab projects, 2 existing buildings that were going to be renovated. If EV cars continue to scale up in the market as they have been, with more REACH codes being implemented, then I wanted at a minimum to be able to accommodate that extra load we would need to add EV charging stations for our residents. After doing this exercise, it became clear that going all electric is a no-brainer. When factoring in the reduced operating costs and the higher loan it would leverage, and all 3 options being in the same ballpark, it's more cost effective to build all electric. There are so many other ways and areas to focus on for value engineering that have larger price impacts than the question of whether or not to go all electric. Materials, waterproofing options, design details. The parking stackers, they added over $1 million in costs all in. They were added because parking was one of the community's biggest concerns. I would personally prioritize value engineering the parking stackers. Parking is often one of the biggest complaints in communities we build in, where many NIMBYs prioritize parking over affordable housing units, unfortunately. It's heartbreaking to see developers who are not going all electric, but they are doing parking stackers just because the backlash they get from the public and they need to go through the entitlement process swiftly. So I encourage you developers out there to VE your parking lifts, go all electric. It's a no-brainer. And so onto the HVAC options we looked at, which are all electric. HVAC is typically electric already, so this evaluation didn't play into the exercise of whether or not we would go all electric. Rather, this was to evaluate energy efficiency, costs, comforts, aesthetics in our pursuit of net zero energy. Let's go through each option now. The least cost possible system was a through-the-wall package terminal heat pump, PTHP, similar to what is found in a hotel room. However, the problem was the through-the-wall PTHP does not insulate the outdoor acoustic noise pollution of the local environment sufficiently, and this Arama option put us in violation of San Jose planning indoor noise standards. The project lies at the corner of Alum Rock and King Road in East San Jose, both major thoroughways with high traffic. Alum Rock is actually considered a California State Highway Route 130. The bus stop in front of this project has some of the highest ridership usage in all of VTA's system. Additionally, this was the first development in any urban village in San Jose. The project was a gateway project into the Little Portugal urban village, and the design is stunning. Adding the through-the-wall PTHPs would distract from the beautiful architecture So it was the least desirable option from an aesthetic standpoint. $630,000 was the lowest pricing option nonetheless. After this exercise and after it was too late to make design changes, Sean informed us of a new Arama Hvac that came to market that had much quieter technology that would have passed San Jose standards. And there are now options that are not through the wall to preserve the beauty of the design. So for you developers that are working on project designs right now, going this most affordable route is a very viable option. The other three options we considered were split systems. Option B was a split system with a heat pump and traditional ducting. It's about $330,000 more than the Hvac. For aesthetic reasons, drop ceilings weren't as desirable as conventional ducting consumes so much space. Option C, this ductless mini split is what we selected as the final specification. It has a single wall mounted fan coil with transfer fans, as opposed to what you will see in option D, which has multiple fan coils with one in each room. It was $60,000 less than the heat pump with traditional ducting. These are the specs of the system selected. Cooling BTUs of 18,000 and heating at 19,000 BTUs. We don't have one in every room. There's just one mini split system in the living rooms for the 1-bedroom and the 2-bedroom units. However, in the 3-bedroom units, we did add a second mini split in the master bedrooms to ensure those larger units would be cool, hot enough for residents. There are also transfer fans in all bedrooms. This is the most luxurious system that would provide the highest comfort. It also was $200,000 more than the system we selected. This is a recap of all the pricing, so you can see the comparisons in one summary snapshot. And on to the lessons learned. So number one, start early. We started the cost benefit analysis during design development phase, and it took months to coordinate with all the different players involved. By the time we learned certain things, it was during the construction document phase when the details in the drawings are much more fleshed out, and making changes trickles through the drawings, takes time, and there are added costs. We were anxious to submit for building permits and start construction as soon as possible. We didn't have time or money to update drawings that late in the game. So you may think it's too early to start during schematic design phase, but if you have an energy consultant on board, they can work with the MEP and GC and solar companies to start evaluating options for equipment and costs involved before you enter design development. Number two, also, if we had started earlier, we could have gotten ahead of the snafus we had with solar. Because of all the compressors on the roof with the mini split systems, there wasn't sufficient roof area for a meaningful PV array. The building had a donut hole in the middle as well, taking away from available rooftop space. In order to get the size of array we wanted to have the greatest offset, we would need to elevate the PVs on a raised canopy. The elevated array would offset 45% of net energy, which is pretty decent. But we were too far along in the design in construction document phase. And like I said before, the added design costs, coordinating with structural, time delays, plus the added cost for the raised canopy, the payback period ended up being over 20 years. And our construction costs were already high, so we ended up not doing solar. If I had started earlier, if we had all started earlier, I think we could have incorporated it. During the design process, we originally wanted to wire the individual water heaters to the house meter, but a miscommunication had occurred and the MEP ultimately did not do that. The architect team had several transitions in staffing on our project, which resulted in this major miscommunication. And when we discovered the water heaters were wired to the units, it was too late in the design process to make that change. It was the construction document phase at that time. So if we had wired the hot water heaters to the house meter like we wanted, then the tenant utility allowance is lower because they don't have to pay those costs. And this translates to higher rental revenue. And that's a huge benefit because we can then leverage a higher loan. And number 4, the rent a tenant has to pay is reduced by what is called a utility allowance that is provided to them. In our industry, we call utility allowances UAs for short. The idea being that tenants have the utilities in their name, pay the bills, but the rent we charge should cover their utility costs, rather than having every tenant submit every single bill for their utilities. That would be crazy and too much paperwork. There are established standard methods of calculating these UAs, utility allowances, that come up with averages. So if a household uses a ton of energy, they only get the same utility allowance everyone else gets based on an average person's usage. Hvac is one of the methods of calculating them. The most common calculation method is one provided by the housing authorities, in which they look at comps and estimate energy costs. I'm actually not 100% positive how they calculate them, to be honest, but I do know how Hvacs are calculated. They're based on modeling the energy loads and factoring in the energy efficiencies implemented for that specific building, whereas the housing authority and other methods are looking at typical average utilities for a conventional home. Quetzal was 45% above energy code, so clearly the utility bills will be lower for these tenants than 1970s apartment unit, for example. In most jurisdictions, Hvac utility allowances are significantly less than the ones the housing authority calculates because they're energy efficient buildings. And so in order for Hvacs to be used as a financing tool, the Hvac UAs need to be lower than the housing authorities. And that's typically what they are. And how this helps financing is that, as I've kind of mentioned several times, by lowering the utility allowance, then we receive more rents. And we have higher income, which means we can leverage a higher loan. And the amount of increase in loan funding will help pay for the solar costs, if not cover it all with excess to offset other costs. So back to, had we rewired to the house meter, we would have been able to generate funding to cover the extra elevated solar array costs. So developers, please look into Hvac. It's a very important tool that can help finance energy efficiency. And then the last one, I think everyone is familiar with this, but it's a really big one. It was very time consuming to do this exercise. If I do it again, and anybody on that team does it again, it will be smoother. Sometimes it felt like we were spinning in circles because of the unfamiliarity of the subject matter. Sean was crucial in guiding us and helping us. There are so many cooks in the kitchen though. As I said before, it was everyone's first experience. So that will just change over time. And how much on time? Am I good? Am I good?
Well, you are fantastic. But you're at about a minute to, it depends on, you should try to do it, finish up in the next couple minutes.
Perfect. Well, I am done. I was, I'd mentioned Antioch briefly before, and I think it's really important to try and convert existing buildings to all electric if possible. So start very early in the design process, because there will be issues with your design team, and that's kind of what prevented us. It was like the main reason, and also the electrical loads. If you can, we were going to use Hvacs though, and then Hvacs would have been able to help fund upgrading the electrical loads. So start early in the design process, and then I'll just end on this slide. You guys can read through it, just some trends that I've already kind of talked through. Thank you so much for having me, Sean.
Thank you so much for being here, Sarah. It's an honor to have a real live developer, 20 years experience, telling us what's up. Your voice is so clear and authoritative because you know what you're talking about. And it's awesome. Thank you, Sarah.